All right, guys, like I said, I'll upload exam 4. I'm sorry, I thought I'd put it up, but apparently I hadn't. I'm sorry. But y'all got your exam 4s back? Is that, you did get them back? Okay, well, I'll upload it with the solutions as soon as we're out here. Um, I'm going to go through all the 4 exams. Remember, as I told you, you should just study the 4 exams from this semester. I take those questions, like I take the multiple choice and I'll change them up a little bit. Change, like the conceptual questions, I might change the scenario a little bit. I'll show you some examples of what I mean as we go through. And then with the others, I can change just the numbers maybe in some cases, or maybe change sort of the scope of the problem, but it's still going to be the same type of problem. So if it's a kinematics problem, you'll still have a kinematics problem. Or if it's like a graphing type problem where you're analyzing a graph, it'll be a graphing type problem. Okay, and as we go through, I'll try to point out some of the changes that you might see on what to expect. So what I mean when I say that I change the problems. The test is 23 or so multiple choice. I'll count it like 25. They're worth 2 points each, so they're worth 50 points total. So there's 5 or 6 points that are built in there already. And then also there are, I think, 7 free response. Is that right? And they were each worth 15 points. No, that must not be right. Yeah, there were 7. Each was worth 15. One was worth just 10. So it was really easy. All right. Do you have any particular questions right now? Or is it okay if I just take it exam by exam? For which one? Number 15. Is that a multiple choice? No. Okay. Part B. Okay, so here what you have is you have this block and it has a certain amount of energy. So the first thing that you want to do is just find what is the total energy, and then I'll get to part B, okay? But part A was important to this question. First, you just want to know what is the total energy of the block, and it gives you the spring constant and it gives you the amount that it's compressed. And so the total energy is the elastic potential energy of the spring. That's 1/2 kx squared. All right, so my total energy is PES. That's equal to 1/2 kx squared. That's 1/2. The spring constant is 100 newtons per meter. And then x was 10 centimeters. That's 0.1 meters squared. All right, so that's equal to 100 times 0.1 squared. That's equal to 0.5 joules. All right, so that's my total energy. And what it does here is it has a force that acts upon it. And this force has a certain amount of work on this object, and that work is equal to the integral of F times dx. And what I want to know is how far does it have to go in order for that work to take away this full 1/2 joule of energy. Y'all with me on this? It's a good question. You're going to see something similar to this tomorrow, so make sure you're up on it. Daniel? The 1/2 joule is the total amount of energy that is that the block has, and then so this 1/2 joule will equal the work. Because when they do a 1/2 joule of work on the block, that means that it's taken away all the energy. And we know that because the force here is negative, and so the force opposes the motion, or the displacement. And so whenever I do that work on the object, it stops. So I'm trying to get a 1/2 joule away. So I say 0.5 joules equals the integral of f dx. That's the integral of negative x to the 1/2. Actually, I'm looking for a negative 1/2 joule because I'm doing negative work. I want to take away that energy times dx. This is going to go from 0 to some final displacement. And it's this x that we're looking for. That's going to tell us how far the object travels. Okay, so I have negative 0.5 equals, what is this? Negative x, 1/2 plus 1 is 3/2 over 3/2, so this is times 2/3. right? I did that right? Yeah, and then I've already applied the limits of integration. It's pretty simple here because it starts at 0. So it's just x, 2/3 x to the 3 halves minus 0 to the 3 halves. So I'm just left with this. And then I just solve this for x. My negatives become positives. This becomes 3 halves times a half. That's 3/4. This is, it's just algebra from here. Equals x to the 3 halves. And then you raise both sides to the 2/3 power in order to find the answer. I don't know what the final answer is. The cubed root of 9/16, whatever that is. Okay? But if you got to this point, I mean, you basically have all credit. There are no funky exponents. So if the exponents sort of throw you for a loop, don't worry about that. You're not going to see that tomorrow. But you will see a problem similar to this, okay? So make sure that you're up on this, on how to find the work due to a position variable force. That's what we're doing here with this integral. Does that answer your question, Harley? Yeah. Anything in particular about this? Okay. That's a good question. Anything from this exam right now? We can come back to it in just a bit. I was going to start with exam 1. All right, look, I'm just going to go to exam 1, and then we'll come back to this sort of in the course of things. Exam 1 was on sort of basic stuff, dimensional analysis. Like, for example, on the multiple choice, you'll have one like this tomorrow, a multiple choice where you have to determine is it dimensionally correct. But instead of these equations, you're going to have some different equations. All right, so I'll give you the same question, but it'll be just different equations. Is that clear what I mean? That's how I mean when I'll change up the questions. Or like, for example, you'll have an estimation problem, but it's not going to be a pencil. It'll be something else, something that's very common to you that you'll know the size of, but you'll have to estimate either its mass or its length. You'll have to estimate its length, okay? You might have a sig fig problem like this. I'm not sure if you do or not, but you might have one, but I would just give you different numbers, and so the answer would be different. Is that clear what I mean by how I'll change up the questions? Okay. All right. Any questions about the multiple choice here? You're certainly going to have to do some graphs. In fact, in the test, in the old test, you actually, in some of the free response questions, you had to draw graphs as well. So make sure that you're up on that as practice that. Any questions about that? Y'all feel pretty comfortable about it? You're looking at the slope. So how does the slope change? Position versus time graph, the slope is the velocity. On a velocity versus time graph, the slope is the acceleration. Yeah? Okay, what particular questions about this test? Exam 1, we had this graphing problem. This was just sort of a basic kinematics problem. An estimation problem. No derivations on the exam tomorrow, so don't worry about the derivations. Here was this given a function, finding a position function, finding the velocity and acceleration, and describing things about that motion. I think that was the end of it, yeah.
So we won't have to derive the kinetic equation?
No, you'll do no derivations tomorrow. All right. Any particular questions about this? 16. Which one was that? This one? All right. So in this one, I give you a graph, and I give you the function that describes it, and you had to answer a few questions about it. Just a couple of things. Remember, if I have a position versus time graph, and I ask you for the velocity like I did here, you just have to find the slope of the graph, and you find the slope of the tangent line. So really, the best that you can, draw the tangent line, something like that. And then you find the slope of that, rise over run. Let's see, so I pick a couple points. I'll use this point, and I'll use, I don't know, I guess, I don't really have a good one. So I'll use this point. And then I find the slope of that. The run is about 0.6, or I'll call it 0.5. The rise looks like it's going from about 2 to 7. So the rise is about 5. And then so my slope here is 5 over negative 5, or 10. So my estimate of my velocity here is 10. But actually it's not 10, it's what? Is it positive or negative? Right, so this has a negative slope, so I'll need to be careful with that. So for part A, I'm just estimating negative 10 meters per second. Now don't forget too, we had another thing where we are graphically interpreting motion, and that is if I have a v versus t graph, right, and I have some function, I can ask you what is the distance traveled, and how do you find the distance traveled? Right, you integrate, or you find the area. Like if you're just doing this graphically, you just find the area. So if this was a v versus t graph, for example, you would say, well, this block is 4 times a half, so this block represents 2 meters. That's only if this was velocity. Clear with me on this? Okay, so that block represents 2 meters, and I have 1, 2, 3, 4 blocks, plus another about a half a block, or maybe a whole block. So I have roughly 9 to 10 meters that it's traveled, if it's a velocity versus time graph. I could ask you something like that as well. That's only if it's a velocity versus time, and this one is not. This one is a position versus time. Okay, and then I asked you to write the function that describes the velocity. Now I give you the function up here, x of t, and so my velocity is the derivative, dx dt. So that's going to be negative 20t plus 20 is my velocity. And then I could double check my answer here if I want to know the velocity at 1.5 seconds, and I think I actually did ask that. I asked the velocity at 1.1 second. But if I want to know the velocity at 1.5 seconds, I just put in 1.5. So I say negative 20 times 1.5 seconds plus 20. So that's negative 30 plus 20, which is negative 10, which jives with what this estimate that I had up here. It's a pretty good estimate, actually. It's exactly right. Okay. Are y'all able to take a function and get the velocity and the acceleration? Yeah? Okay, make sure that you're able to do that. It shouldn't be a surprise that you'll see it tomorrow, because it came up several times on various exams. Let's see, what is the acceleration of the object? Well, if my velocity function is negative 20t plus 20, then my acceleration function is just negative 20, just taking the derivative of that velocity function. And then how long is the object in motion? With this particular one, it said that it came back to its original position. So a really easy way to do this is just say, well, it's in the air for 2 seconds. And I would have taken that as an answer in this one. Or you could also take a more complicated thing. How did some of y'all do this? Or you could treat it like a projectile motion problem, where you have what would you say? Where you say like v top equals 0, and then you find the time to get up to t top, which it turns out to be 1 second, and then you just double that to get the total time. Okay? And then E I've already answered. How to find the velocity. You just plug in the time at a particular time. Is that clear on this one? Who asked about this? Michael? Is that clear for this? Yeah, I understand. I am, yeah. I'm going to post it online. Okay, well, you'll stop me if I'm unclear on something, or if you just don't get it. We have plenty of time. Okay. I would like to warn you that we had this, this was largely a free fall problem, but I have put a problem on that's or never mind. We'll get that. That was from exam 2. Never mind. I'll get to it when I get there. Okay. Anything else from this exam? Oh, yeah. Let's see. Let's see. So when say this is the snowdrift right here, and the airman, he strikes the snowdrift, and then he travels another 3 meters. And I just want to know how long it takes him to travel that 3 meters. And in the previous one, you find his velocity here. That was v final from part 2. That becomes our v initial, right? Right, yeah, so is that how we did it? Yeah, we say v equals v naught plus, oh, no, I don't do it that way. I say that y equals v naught t plus 1/2 a t squared. Oh, no, and then we also had to say that v is equal to v naught plus at. Okay, so here our v becomes 0, as you said, because he comes to rest down here. This is v equals 0. And then this becomes a system of equations, because look, I have 2 unknowns. I don't know the time, and I don't know the acceleration. And those are the only unknowns that I have. I don't know time, and I don't know acceleration. And I'm looking for the time. So what I do is I solve this for a. I say a is equal to negative v naught over t. And then I take this, and I plug it in there for a. And then I can solve that system of equations for t. Fortunately, the t squared here goes away, so I don't have to use the quadratic formula. All right? Let me go ahead and write it out. So y is equal to v naught t plus 1/2 negative v naught over t times t squared. And so I lose that t. And now I know everything except for t. Because I found v naught. I forget what v naught was in part B, but I find v naught in the previous section. And so when I solve for v naught here, for part D, when I want to come back and find that, I just come back and I plug in my v naught, or excuse me, I plug in my t right here, which I find in part C, and then I can find my acceleration. This problem I did not put on the exam, not explicitly, but some of the things that you do in this problem are important for other problems, so it might be worthwhile for you to go back and take a look at. All right? Any questions? I'm not going to tell you everything on the exam, but I'll tell you some things. Can I clear this? I took a couple problems from each exam. As I said, there are 7 problems total, so. And there are no equilibriums, so the take-home problem that you had, you won't see that on the exam at all. Yeah. No statics, no equilibrium statics. Let's take this away. So far, no derivations, no statics. Okay, let's go to exam 2. We can always come back, like if you forgot a question, then let me know. So again, on these things, these conceptual problems, for example, the way I could change them, like if you saw something like this, I could just change the direction of the vectors. It'd still be the same problem, but I'd change the direction of the vector. So make sure that you can do things like that. Like something like this, I could change the scenario, or maybe put position versus time instead of velocity versus time graphs. Change the numbers. Well, I don't know if I had, yeah, could change the numbers on something like this. Any particular questions here? Exam 2. Here we had vector analysis, adding up 2 vectors numerically. Projectile motion. We had this force problem with a system of equations. Another force problem here, Newton's laws. And that was it. So for example, I could take something like this and change the forces that are acting on it, or likewise something like this problem, change the forces, but it would still be an inclined plane, or it would still be a problem like this one down here where I have a frictional force. Similar problem, like you would recognize it, but the numbers would be different. Some of the forces would be different. Okay? What in particular?
No, the multiple choice. I didn't understand
Yeah, not many people got that one. So you're in good company, but you won't see it tomorrow at all. Is that okay? I could go into the explanation if you want, but
That's fine.
I don't think it's terribly important. It is on the concept test if you want to look back, but it's just looking at how F equals ma, how if you change one of those values, how it changes the other value. Is that okay enough of an explanation? Okay. I don't mean to slap it off, but all right. What else, yo? Number 16. Make sure you're up on your projectile motion, okay? So in this one, you had two objects, and anytime you have two objects, you're going to have two sets of equations. Okay, so you want to treat each object separately and just draw all the forces that are acting. So here we were looking for, that's what we were looking for, the frictional force on block M1, M2, and then the acceleration of block M1, which is also going to equal the acceleration of block M2. So you want to start by drawing your forces. So here I have the force weight of block 2. That's equal to 100 newtons. And then I have the normal force of block 2, which I also know is going to be 100 newtons because I have those equal, they have to be equal and opposite forces. And then I have a tension over here. That same tension is going to be acting on this block as well. And then I have a frictional force over here, Fk. Now I know that this is equal to mu k times the normal force. So since I know this is 100 newtons and this is 0.1, I can go ahead and write that in and say that that's equal to 10 newtons. Okay, it is accelerating. So the tension here is, this tension is not equal to the kinetic frictional force. Now I can write Newton's second law, sum of the forces in the x direction equals ma, x. So that's going to be Fk minus Ft equals the mass, which was 10 kilograms, times the acceleration. I'm going to put in a negative acceleration here. It's negative a to the negative ax because it's to the left instead of to the right. Is that right? Yeah. And then we do the same thing down here for our inclined plane. There's my axes. I have the weight, Fw2, which is equal to 200 newtons. And then I have the normal force here. I'll call this this is Fw1. This is Fn1. I have the tension acting here. And then I also know that I have a kinetic frictional force, Fk1. So I need to find my normal force, Fn1. Well, first I would just draw my vectors. I have Fn1, Ft, Fk1, and then I resolve that Fw1 into its components. That's 200 sine of 60. And 200 cosine of 60. Are okay on finding x and y components of your vectors? You will have to do with force vectors in 2 dimensions. It may or may not be a inclined plane, but you'll definitely have to deal with this and solving the equations. So let's see. I have Fn1 then is equal to 200 sine of 60. Do you need me to step through all the steps here? Okay, I will. All right, so 200 times sine of 60, this is 170 newtons. All right, I just get that because I know that this force has to equal this force because those y forces have to be balanced. And that's important because when I find Fn1, then I can find Fk1. That's going to be mu times Fn. My mu is 0.1, so that means that Fk1 is going to be 17 newtons. I just multiplied this force times the coefficient of kinetic friction. And so I can write in here I have 17 newtons. Okay, and now I can write my sum of the forces in the x direction. run out of space here. I'm going to write over here on the left. So the sum of the forces in the x direction is going to be 200 cosine 60 minus ft minus fk1, which is 17 newtons. And that's equal to the mass of block 1 times the acceleration of block 1. Okay, so now I have two equations. I have this equation, which has two unknowns. I don't know ft, and I don't know a. And then I have this equation up here, where I don't know ft, and I don't know a. And what you have to do then is solve that system of equations. I'm not going to go through the system right now. In fact, you're not going to have to solve a system of two equations tomorrow in the same way as you did here. Is that clear what I mean? Or you can take this problem and make it simpler where you don't have to do that. But you would solve the system of two equations where solving one of them for, let's say you're looking for t, I think you're looking for both of them. Solve one for, say, ft, and then plug that into the other one. We've done that several times. Is that okay? I can, if you want, we can stay afterwards. I can help. We can go through that again in more detail. But then once you do that, then they all start falling out. Yeah, Daniel? M1 is just 20 kilograms. Yeah, so when you're writing those two vector diagrams, you treat each block separately. So it's as if the other block doesn't even exist. So M1 is this mass, and then this mass, which was M2, was just this mass. Does that answer your question? Oh, for the acceleration? Right here? You would use 20 kilograms, yeah. So use the full mass. There's no cosine 60 here. All right. How you on that? Okay. Your problem tomorrow will not be quite as complicated as this if you have an inclined plane, or even if you don't. But you will have Newton's second law. Can I clear this? Okay. What else on this test?
Number 15.
Okay. So here I have a stone that's thrown outward from a 20-meter high cliff with an upward velocity component of 10 meters per second. So I have a cliff. So I could give you this question, by the way, and just give some of the different things, like not give it to you in the same way, but it would still be a projectile motion problem. I have this object, it's thrown outward. It follows a path like that. I want to know the total time in the air. It lands 100 meters from the base of the cliff. I want to know what is the angle, and then I want to know the magnitude of the ball's velocity when it reaches the ground. So the first thing is I know that Vy is equal to 10 meters per second. Usually in problems I give you the velocity, but here I gave you just the y component of the velocity. So all you know is what is this particular component. But I know that that's 10 meters per second, and then I just want to know how long is it in the air. Well, I also know that this is 20 meters. And so I say that y is equal to v naught y times t plus 1/2 ay t squared. I know to use that just because I know everything in that equation except for t. And the way you do that in these problems, you write down everything that you know. And then you can write your sets of equations over on the side and then say, well, which equation would be best to solve this? And usually one will pop out. And here, since I know y, I know v naught y, that's this vy component, and I know the acceleration in the y direction, then I can solve this. So I have negative 20 equals v naught y, that's 10 times t minus 5 t squared. So I get 5t squared plus 10t minus 10t plus 20 equals 0. And then you had to use the quadratic formula to solve that. Was it a simple thing? T? Oh, yeah, you're right. It is minus 20. Was it a simple answer to this? Like 2 or something? 20? No, it's not 2. 3, 4. I don't know what the answer is right off, but 3.24 seconds. Okay, so you get, when you use the quadratic, you solve that to be 3.24 seconds. Y'all okay on the quadratic? You just want to put it in this form. This is A, this is B, this is C. And then you plug it into the quadratic formula. All right, and then if it lands 100 meters from the base of the cliff, so if this is 100 meters, I want to know what is the ball's initial velocity. Well, then we're looking at our x component, and I know that x is equal to v naught x times t, and that's equal to v naught times cosine of theta times t. And here, I don't know v naught, but I know v naught y. So I say v naught y, which is 10 meters per second, is equal to v naught sine of theta. So there's a little bit of sort of trig gymnastics you had to do here. So I say 10 equals v naught sine of theta. And since I'm looking for theta, I'm going to solve this for v naught. So I'm going to say v naught equals 10 over sine of theta. And then I'm going to take this and plug it in for v naught. So I get 10 over sine theta, cosine theta, t equals x. And now I know everything here but theta. So I know that x is 100 meters. Cosine over sine, or sine over cosine is tangent. So I'll just do 10t over tan theta. I gave you that trig identity down below. And then I know t now, right? I know t? Oh yeah, we know t from right here. And then we just plug that in, and then we solve this for theta. You have to do an inverse tan there to find theta. I think y'all are probably okay with that. All right. The exam's longer. Like some of the, like I said, the gymnastics with trig and algebra aren't quite as complicated on the exam, on the final exam, because it's just longer and there are more questions. So I've tried to simplify that as much as possible, but still keeping the basic ideas behind projectile motion, Newton's second law, all that business. So if you're scared away by the, like I said, the trig or the algebra, don't be too terrified. It won't be this complex. But I think y'all can do this. You have the ability to do this. Okay? Is that okay, Courtney? Can I clear this? Oh, and then, to find t, the magnitude of the ball's velocity, when it gets down here, it has a vx and it has a vy, and you have to find both of those. So vx is equal to v naught cosine theta. And by this time, you'll have theta, and then you can find v naught from this. And then vy is equal to v naught y plus ay times t. And since you know t, then you can find vy at the end. And then to find the magnitude of two vectors, you just use the Pythagorean theorem, the square root of the first vector squared plus the second vector squared. All right. What else on this test? Or should we go on to exam 3? All right, I'll go on to exam 3, but if we want to come back at the end, we'll have time if you think of a question. Is this helpful for y'all? Okay. Let's see. Energy and work here. We've already done some of these. I said I could sort of change the wording on some of these. If I've just changed a single word, but it changes the problem, I've tried to bold and highlight it and make it big, just to be clear. So, any particular questions? We worked this problem earlier. We had conservation of energy here, work. dot products. You'll have the equation sheet that you had on the last exam. So even though this exam covers chapters 1 through 4, the equations from those chapters won't be on your equation sheet. What you had in the previous exam, you'll have tomorrow. Conservation of momentum, simple collision problem we had here. Impulse and momentum, the force, F equals delta P over delta T. Sort of business. That was it. This was probably the easiest of the 4 exams. You don't think? Or maybe the 4th one was the easiest. But there were some sticking points. If you have a conservation of energy, you just want to start out the problem asking what type of energy you have at each location. So here, for example, because it was V was equal to 0, I know that here it only has potential energy. Here it has potential energy and kinetic energy. Like, for example, down here, because the height is 0, it will only have kinetic energy. And so whenever you encounter a conservation of energy problem, either this one or the spring problem in the next one, you want to ask yourself, what types of energy does it have at different locations? Sure. So here, I want to know the speed of particle at point B, and then also at C, and then how high does it come when it comes up here. So I know that my potential energy here is equal to mgh. It has no kinetic energy at that location. And down here, it has potential and kinetic because it's moving when it gets to that location. So that's going to be mg times h, which is 2 meters, plus 1/2 mv squared. And here, h, by the way, was 10 meters, which was given. All right, and then you just solve for v. All right, so once you get sort of how the energy is allocated, it's fairly straightforward. My m's cancel here. Your m's always cancel in these gravitational problems. However, in the next one where you're dealing with a spring, your mass doesn't cancel. So just make sure you're clear on that. This is 110 times 10 equals 20 plus 1/2 v squared. That's square root of 160. Which is like 13 point something, right? No, 12, roughly 12. Between 12 and 13, right? 12.6, okay. So 13. Okay, and then at point C, this is different because it only has kinetic energy here. So you would say the potential energy, mg times 10 meters, is equal to 1/2 mv squared. That's the velocity at point C, because it only has kinetic energy. And then you'd solve for v. And on the right-hand side, well, we can tell right off what the answer is, because here it's not moving, it only has potential energy. So when it comes over here, it's going to come up to a point where it only has potential energy, and that will be the same point. Now, recognize that if the velocity was greater than 0 here, it would come up to some higher point, because it would have enough energy to get up to that point. You follow what I mean by that? Okay. Is that okay, Christian? Yeah, okay. You'll certainly see a conservation of energy problem, right? We had a couple on this test. This one and the next one were both conservation of energy problems. So you'll certainly see that principle. Alrighty. What else on this test, Joe? This one, we've already done this one. 16b. Okay, this one is related to the work energy theorem. Once you know the amount of work done here, this position is the same as this position, then you know its energy. How much work was for part A? You know, how many? So I just had 1 joule here, and so that work is all converted into kinetic energy, which is 1/2 mv squared. So if I want to know the velocity or the speed, I just say 1 joule equals 1/2 of m, which is 2 kilograms, times v squared. So v was equal to 1. Okay, because whatever work you're doing is changing the energy of the object. And here you're doing positive work, which causes the energy to increase. It all goes into kinetic energy, which gives you, that kinetic energy is 1 meter per second for this 2 kilogram object. All right? Is that okay, Michael? All right, what else in this test? 16. You okay on these collision problems? Initial momentum equals final momentum. I think these are fairly straightforward. Yeah? Okay. All right, let's do exam 4. And again, we can come back if you want. I think there are fewer problems from this exam because we didn't cover as much material on this exam. And as I said before, unless you came in late, there was none of the take-home stuff on the final. So no derivations, no take-home, no equilibrium problems. Any particular questions here? $14. Okay, this is a conservation of momentum problem. Initially, nobody's moving, right? So my initial momentum, Li, is equal to 0. So then I know also that my L final has to equal 0. And what you have here is you have this guy, and he's swinging this thing around his head like this at a certain speed, 1.2 revolutions per second. And so this has a certain amount of angular momentum. And so that means that since the total angular momentum has to be 0, the guy is going to have an opposite amount of angular momentum. So the guy will have an angular momentum that's equal but opposite that to the ball. And so we could work this out. We could say Li is equal to Lf. Li is equal to 0 because nobody's rotating. Lf will equal the angular momentum of the ball plus the angular momentum of the guy. And then we have to find out, well, what is the moment of inertia of the ball? That's going to be mr squared. I treat it like a discrete particle, right? So just the mass times the radius squared times the negative 1.2 revolutions per second. Negative because it's clockwise, plus the guy, he has a moment of inertia of 100 kilogram meter squared times his omega. And then I have to figure out what is this moment of inertia. I have a 1 kilogram mass on a 2 meter string. That's 1 times 2 squared, so it's equal to 4. And then I know that this is equal to 0, and so I solve then for omega. I have negative 4.8 plus 100 omega equals 0. And so omega equals positive 4.8 over 100 0.05 tens hundreds, right? Yeah, 0.05 revolutions per second. I'm sorry, y'all can't really see that. Can you see it okay, Courtney? Michael? I'm sorry. Okay? That's a conservation of momentum. Initial is equal to the final angular momentum. All right? What else on this test? Okay. Okay. Well, you sort of have to work through part A. Does anybody know what the time is for this one? 4 seconds. And then you want to know how many revolutions does it take for it to get up to that speed. And so I say theta, right? I know it's theta because it says revolutions, equals omega naught t plus 1/2 alpha t squared. I know that omega naught is 0 because it starts from rest. And this is my angular acceleration. And so that's going to be 0 plus 1/2 of 2. However, well, we'll just go ahead and get it in radians. Radians per second squared times t, which is 4 seconds. And so that's going to give me 16 radians, but I'm asking for the number of revolutions. So 1 revolution is 2 pi radians. So that's 8 over pi, which is roughly 16. 2.5, 2.5 revolutions. What was the other question, Michael? What was it? Here, I'll scroll down. What is a centripetal acceleration? So I can find my centripetal acceleration a couple different ways. In this problem, you had to find the linear speed, but there's an easier, and when you do that, you can find the centripetal acceleration. You can say AR equals V squared over R, and then you just plug in that V, and then the radius, which was, I think, 1.2 meters. Or you could say AR is equal to omega squared R. That's not on your equation sheet, but when you say V equals omega R, and plug that in here, then you get this expression for the centripetal acceleration. So you can just say 8 radians per second squared times the radius. Wasn't it 1.2 meters? Is that what it was? Okay, yeah, so that's 64 times 1.2. I get 77 meters per second squared. Was the radius 1.2? Oh, okay, so 0.6. Right, so I'm going to get instead, what, 38.5 or 39. I don't remember if I probably, yeah, I probably didn't count off. I mean, did I count off anybody else? Did you? Okay, yeah. So I probably just, what, the question is this the diameter or is this the radius? It's not even obvious to me here. I probably didn't count off. Yeah, that wasn't very clear. Did I count off on anybody? I don't think I did. Okay. But you understand the difference? Everybody follow? Yeah, I'll be more clear. Okay, anything else here? There's a lot on this test, but it'll be pretty straightforward. It'll look a lot like your old test, with some changes, of course, but it'll be very similar. Okay. Any other questions? Okay, shoot. Guys, like I said, the help session, you can come and go as you like, so feel free to go if you like. Which chapter are we looking at, Daniel? That sounds like chapter 3. Was it projectile motion? This one? Okay, I forget. Did we let his angle equal 45 degrees in this? Yeah. So this is a projectile motion problem. I have this guy. He's traveling at 60 kilometers per hour. Let's see. I want to convert that to meters per second in 1 kilometer. There are 1,000 meters in 1 hour, 3,600 seconds. On the exam, there aren't a whole lot of extraneous conversions. So that's 17 meters per second. And it says that he goes 39 meters down the road. So that is my x displacement. And I just want to know... Oh, no, he wasn't. That's not his speed here. I'm sorry. That's just the speed limit. So I'm not given V naught at all. But I want to know what V naught is. And so I say x equals V naught x times t plus 1/2 a t squared. I don't know t, and I don't know V naught. So I'm also going to have to say that... Is this going to work? Yeah, it should work. Right, because there is no x here. And then I'm also going to say that Vy is equal to V naught y plus AT. I'm still going to have 3 unknowns. Was there a third equation? I don't remember this. Do y'all recall? There must have been a third equation. Let me think. Because I have 3 unknowns here. I have V naught, theta, and t. All are unknowns. I don't remember, Daniel.
Initial y velocity times t plus 1/2 a t squared.
Wait, what now?
Y equals initial y velocity times t plus 1/2 a t squared.
I don't know my y displacement. I don't remember. Okay, and then we can substitute that in for V naught. I'm sorry. It's befuddling me right now. We can look at it later. But you will see projectile motion, but it won't be like this. Right. Yeah. As I said, you're not going to see something, at least mathematically, something that complex. All right, Daniel, I'm sorry. Is that an okay answer? Sorry, I sort of shut down after about 10:30. What's up, Michael? Yeah, it's going to be the same as last exam. Right. I get up at like 3, so that's basically my whole day. Okay? Any other questions, y'all? This is helpful for you? Worth an hour of your life? Okay. All right. I'm going to post this, so if you miss something, you can catch it later.